Hi. In this video of import, we are going to be starting with higher order differentiation. Now, from this unit up until the rest of your syllabus, we are kind of going to be doing things which you're already familiar with. In terms of concepts, differentiation isn't something that you haven't studied before, and the idea of these units is to reuse the concepts that you're already familiar with and put them into the familiar lens of or I should say mildly familiar lens of economics, microeconomics in particular, and get to a point where we are able to explain, some of the microeconomic phenomena that you observe in terms of, the mathematics that kind of follows along with. So for the rest of the 4 units that we have, or 4 sections that we have, particularly higher order differentiation, convexity and concavity, constrained optimization as well as unconstrained optimization. The major concepts that we're going to use are going to be that of differentiation. Let's get started. So when you start with higher order differentiation, the first thing that we sort of look at is that if a function is differentiable, then f prime x or dy by dx is the first order derivative, and f prime of f of basically del f by del x. So d upon dx of del f by del x is your second derivative, so it's d2y by dx squared or f double prime x, and so on and so forth. This is notation that you're already familiar with. Now the idea is that if you were to go to, so the second order derivative is f double prime x. If you were to go to the third order or the fourth order, they would be represented by the equivalent number of dashes of sorts that you see. So instead of double prime, it will be triple prime, and so on and so forth. Okay. So, to consider an example, if you have f of x given by this particular function, f double prime of x, f prime of x, and then f double prime, and then f triple prime are calculated in the following manner. Like I said, the underlying concept is that of differentiation, which is not very difficult, but the idea is that, when you're calculating so because this is a single variable function, there's not much of a problem. But when you're dealing with multiple variable functions, then you're supposed to calculate such f double prime x and f double triple prime x and so on and so forth. The idea is to always consider the other variable as constant and then to calculate fxx or fxy or whatever it is that is relevant for your case. So that concept is precisely known as that of partial derivatives. Given a function y is equal to f of x, the derivative f prime x represents the rate of change of the function as x is changing. For a function of 2 variables, one variable could be changing faster than the other variables, and it will be completely possible for the function to change differently with respect to each of these variables. So, like I said, when you're dealing with 2 independent variables, the partial derivative z with respect to x can be formed, with normal rule of differentiation. The only difference is that you treat y as constant, and vice versa when you're doing it with respect to y. So the notations for partial derivation are given as follows. When you have a particular function given by z is equal to f of x comma y, del z by del x is given by fx, del z by del y is given by fy, and so on and so forth. I mean, it's either small f in both places or it's cap f, you can take either. Again, so for a function like this, if you were to calculate del z by del x, it would be something like 4x cubed y squared minus 2x y to the power 6. And similarly for fy. Now for a function z is equal to fxy, f prime x and f prime y are the two first order partial derivatives. Since z is a function and f prime x and x prime y are also a function, second order partial differentiation for differentials can also be found. Differentiating of this function first with respect to x and then with respect to y is called the mixed partial derivative. The various notations for partial derivatives are given in this table. You have fxx, fyy, fxy, and fyx. Now, you will also study something known as the Young's theorem, which would tell you that the values of these two are actually equal. But, we'll get to it when we get to it. Basically, the point is that a function has 4 possible second partial derivatives, which are obtained by derivating with respect to x and y, and y and x and so on and so forth. And the interpretation of these signs are going to be given as follows. I'm just going to take up one as an example to sort of explain this to you. So take this as an example. When you have del 2z by del x square, if it is positive, then what you're saying is that the slope in x direction increases as x increases, given y is constant. If it's negative, then you're saying that the slope in x direction decreases as x decreases, and again y is constant. So the second derivative gives you the rate of change of slope, right? So rate of change of slope versus the first derivative actually gives you the slope. So that's the way you should sort of differentiate between the two. Okay. Now you have z given by this function, and you were supposed to find del 2z by del x square, and you have to interpret the result. I'm sorry about the spelling. Interpret the result. So if you calculate del z by del x, it's just going to be 0.5 x to the power minus 0.5 y to the power 0.5. Okay. So this is del z by del x. And then if you were to calculate del 2z by del x square, that's just going to be equal to minus 0.25 x to the power minus 1.5 y to the power 0.5. So once you're, when you have this, so you can clearly see here that if x and y are both positive, then this is going to be greater than 0. At the same time, if x and y both are positive, this is going to be less than 0. So, saying, considering x, y greater than 0, what you can say about these two things is that the first thing that you can say is that as x is increasing, the function is going up, or, so as x is increasing, the function value is going up. But the rate at which the value is going up is actually falling. So the function value is increasing at a decreasing rate as x increases. So this is exactly what you have here. Now another example that you can consider is this particular one right here. You can calculate fx, fyx, xy and fyy and so on and so forth, and you can also see that fxy is equal to fyx. I'm not going to be doing it because this is sheer arithmetic. Okay. Now the two mixed second order partial derivatives, also called as the cross partial derivatives, are always equal when fxy and fyx are continuous. This is explained by the following theorem given by Alexis Clairant, also known as the Young's theorem. This was something I mentioned earlier also. So the Young's theorem basically states that if fxy and fyx are continuous, then fxy is going to be equal to fyx at all points a, b. You don't have to worry about this disk business. This is nothing. It's just, remember the Young's theorem as saying precisely the fact that your mixed partials are equal given continuity. Okay. Now, one of the questions which you rarely ever get, but this is one of the questions that, is sort of like the starting point for questions on Young's theorem, is to verify the Young's theorem for a particular function. There have been times when this has been asked as a very small question, where, basically you start by, stating the Young's theorem, which is to say that, in case of continuity, the partial derivatives are going to be equal, and then you calculate them and verify the theorem. So that's exactly what you've sort of done here. I'm not going to go to the calculations of this because this is again sheerly differentiation. So the solution's right here for you to work it out yourself. But I would suggest stopping the video and sort of working it out instead of skipping the calculation, because it doesn't always do good to be confident, especially when you're dealing with a function where you have e to the power minus x square y square. Okay. Now the Young's theorem can be extended to any function of n number of variables and their mixed partial derivatives. The only thing to remember is that in each derivative we'll differentiate with respect to each variable the same number of times. So for 3 variables you will have F11, F12, and so on up until F1n, F21, F22, and so on up till F2n, and so on and so forth. For n variables, you can generate a very similar whatever matrix. This matrix is known as the Hessian matrix. The Hessian matrix is basically the matrix of second order partial derivatives, which are written in the following manner. So the Hessian matrix is something that is going to keep popping up for you guys. There are multiple places in which the Hessian condition is used. For a three variable case, the Hessian matrix looks something like, so if you had x, y, and w as your three independent variables, then it would look like, fx, y, fxw, and fyx, fyy, fyw, fwx, fwy, fww. Okay. The idea is always that, across the diagonal you will have no mixed partial derivatives, but actually the partial derivative with respect to itself. And, all along these diagonals you will have mixed derivatives. This and this would be equal, this and this would be equal because of the Young's theorem aspect. And this would be equal because, again, of the Young's theorem aspect. Okay. So that's it for this video. Thank you.